the other thing that we kind of need to know about, but there isn't any practice questions on, is Einstein's theories of relativity. That's another topic. Einstein says that, well, if I'm standing on Earth right now, and I stand on a scale, if I'm standing on a scale, it might say I don't know, 100 newtons. Obviously not, because that's too small, but fine. However, what if I am in space and I am standing on a scale in space? There's nothing around me. What will it say?
Less.
Less. There's no gravity pulling down, because obviously gravity pulls down, right? In space, that should say 0. However, what if I am on gravity, and let's say this is a trap door. The door opens. I fall down. I am now falling in space. I am falling, not in space, on Earth. I fell off a building, for example, and there is my thing there. What will the reading on the scale be now? Will it still say the same as before, 100?
No.
No. Actually, if I'm in free fall, I am not applying any weight. It'll just be 0. If that is the case, that means free fall is kind of similar to that, to being in space. So if I was to ignore everything flying past you as you're falling down, you would be weightless. So then that takes me back up to here. Well, it didn't take me, it took Einstein back up to here, because this is all his idea. He said, what if I closed him in a room? He's in space and he has no idea what he's doing. And then I lifted the accelerating, the thing, whatever this is, I accelerated up at 10. What reading should this say? We're assuming this is also 10, by the way, newtons per kg. I'm raising this at the same acceleration as gravity. This should say that, right? You'd expect that, right? Because the gravity is pulling down, and that's why I have 100. Here, I am pushing up. The floor is pushing up at the same amount, so I will still say 100. But I am now accelerating upwards. So then, of course, if you were to shine a light, like a torch, a flashlight, you will shine a light on a wall, it will be pretty much a straight line. What would happen now if I shine a light on the wall here? If I shine, that's a gun. That's not supposed to be a gun. If I shine the light, will it be a straight line as well?
No.
It'll kind of curve, right? Because I'm moving upwards, yeah?
Yes.
So that breaks Newton's laws. Newton was he was amazing. He made all these different predictions and things. He made his rules for mechanics. But then Einstein says, well, if you approach the speed of light, all of your rules, they kind of don't make sense anymore. It doesn't work. And nobody actually believed Einstein. This was when he was younger. He wasn't famous at the time. And nobody believed him. They laughed at him and they said, forget you, go away. How are you going to go against Isaac Newton? Do you think you're Newton or something? That's what they used to say. Now we say, do you think you're Einstein or something? Before they used to say, do you think you're Newton? Well, Einstein says, no, I am better than Newton. So then he decided to figure out how this actually works and what the case is. He then realized something called general relativity and even special relativity. He says that if you're approaching the speed of light, the space and the area around it, actually the time it bends if you have some sort of mass or gravity. So on a planet Earth, or if you're a weightlessness in space, or if you're looking at the sun or a planet, light normally travels in a straight line to find the fastest path. But because this curved, it means the fastest path might not have been a straight line. It would have been a curve. The fastest path would have been in a curve like this. And that's telling me light bends around this object, and because of the gravitational force. And you will know what I mean by fastest path is if you were on one part of the planet over here and you wanted to go here and you were trying to go in a straight line, you would have to go around the curvature of the Earth because the Earth is round. So the quickest actual path would probably be like a curved path like this. If you were to try to go straight, because the Earth bulges, it will take longer. So airplanes, they know that. So they take that into consideration and take an alternative route. The same applies to light around masses and objects. So he did some complex calculations that we don't need to know about, and then he made these things and figured it out. And he showed, actually, I can show you like that. Gravity space around objects, light will even bend around it. Light will move. But then some scientists decided to look at the sun, and they noticed something. If Einstein's crazy numbers are correct, we can apply it to the sun. There were two stars here and here. And as the sun passes through, according to his calculations, if the light bends, the stars should appear further away than they actually are. This is where they should have been. And as the sun was moving in the night sky, or not night sky, the daytime sky, whatever, it was moving, the stars actually did appear over here. They did over here and here. According to the calculations, they were exactly where he predicted them to be. And this made Einstein famous. He put his name on the map with this theory of relativity. And that's why he is a famous guy now, and we use a lot of his stuff. We know that the space and time will bend, which means if you are near somewhere where gravity, time is bending. What does that mean? Time is moving a little bit slower. For the speed to be constant, the time has to move slowly, because speed is the speed, right? Speed is distance over time. The speed to be constant, the time has to change. So that means if I am standing on Earth and I have a twin, I know we have a few twins in the school. If we were able to do this, I would love to test this out. We'll take one twin, leave her here, and send her other twin, the annoying one, the one who I'm talking about knows who it is. I'll send the annoying twin into space and let her stay in space for a while. She will go around the Earth in space, spend some time, and then eventually, when I feel like it, I'll bring the annoying twin back and we will have the twins standing next to each other. I will say, take out your watch, check the time on your clock. Because time was slower on Earth, the one in space actually had a clock that was moving faster. She traveled forward in time. Actually, the time taken for her was not the same as her, so which technically means she is older than the annoying one. The annoying one is younger than the not annoying one. So that's interesting. Time travel's different, so technically you can time travel only in one direction, only by a few milliseconds or whatever, but it's possible to that extent. So the time difference is important. Now, that's even more important in black holes. If you have a black hole in space, big, dense place, where it is so dense that even light can't escape it, and if something was to try and pass through the black hole, it will be very distorted. And you can guess the black hole's there because of distortion of the stars and the galaxies behind it. If you were to approach a black hole, the closer you get, the slower the time is. It will get to a point where you stop aging. Time stands still. You're watching the black hole, you're falling into the black hole. So let's send the annoying one out again. That annoying twin will go into the black hole and she will see everything moving at her normal speed. She will not know what's going on. She doesn't know time has slowed down. She's looking at her clock and the clock is ticking as normal. But the not so annoying twin, she is watching from the side, looking at her and looking at with her clock. She will see that because time has stood still for her, she will not see her slowly disappear into the void of the black hole. No, what she will see, because her clock is moving faster than her, she will disappear just like that. She'll be gone. 1 minute she's there, 1 minute she's gone because of the time difference in this. Because her time will be ticking faster than her time because gravity here is much stronger than it is on the Earth. Black hole has very, very strong gravity. Is that making sense, what I'm saying so far?
Yes.
Or have I lost you in the chasms of space? One final thing I will say before I stop. The last thing is the general idea about here. Why this is useful to us after doing all these Einstein's calculations was this. We have GPS satellites in space and they're sending signals to our phone so we can find out where the nearest McDonald's is. So we're using that to figure out how to get there. Because time moves differently in space, time is a little bit quicker in space than us, it will not accurately track our location. It will accidentally send us to KFC, which we definitely do not want to go to. So that's why we need to be accurate so we can go and have our nice fish fillet or Big Mac sandwiches in McDonald's. So we need to account for the change in time using Einstein's calculations so that the GPS will send us to the correct destinations. Does that make sense?
Yes.
I should have probably recorded that for everyone else as well, but oh, it's still recording in the main meeting. That's fine. I'm going to stop there.